All right, let's start. Good afternoon, everyone, and welcome to another lecture. Today is our final lecture in the fall term, and it's also the first lecture in entirely new area of nanophotonics that we are getting at with this lecture. So if you remember, last 12 lectures, we've been discussing things like, first of all, we discussed the fundamentals of electromagnetics, then we discussed the primitive propagating solutions such as plane waves and various superpositions of plane waves, cylindrical beams, Bessel beams, Gaussian beams. We discussed what happens to waves at interfaces. Then we discussed the class of waveguide structures and periodic systems, wave propagation periodic systems. And lastly, last 3 lectures, we've been looking at various radiation problems, including sources in free space, sources near interfaces. And last week, we finished with the concepts of density of states and partial factor. And that, the last lecture finalized the set of 12 lectures that are united by the idea of propagation and basically the absence of scattering. What we had in those lectures was some kind of precursors to what we're going to do today and the entire next term. So today we're going to start looking at the scattering problem. And this is going to be the subject of almost the entire spring term. Today is only the first lecture that is going to give you some preliminary knowledge of the mathematical framework that we're going to need in the next term. And then after the winter break, after the exam, if you pass the exam, hopefully, we're going to get to the scattering problem itself, and we're going to start solving it, developing different tools to solve scattering problems in various geometries, and examining interesting non-trivial effects that take place in the when light is getting scattered by a certain resonant nanostructure. Okay, so let's jump into the scattering problem. Let's formulate the scattering problem itself. Let's start with that. So we're going to be considering a linear object, a scatterer, something that can be a film, an interface, a sphere, a dielectric rod, some kind of a cluster of particles, anything that is different from the homogeneous environment. So we're going to have a linear stationary object characterized by a certain permittivity, epsilon s, that can be complex valued, and that can depend on frequency, and that can be homogeneously distributed in space. And then we're going to illuminate this object, this scatterer. I'm going to refer to this thing sometimes as the object, the scatterer, the obstacle, the structure, the anything that perturbs our environment. So this thing is illuminated with some incident fields. The incidence field satisfies the wave equation with the permittivity epsilon h, which is the host medium permittivity. This is the permittivity in the absence of any object. So this is epsilon h, which is assumed to be real valued, non-dispersive, to make things simple. Okay, so we remove this object, and the incident field satisfies this equation. And we solved already that equation, and we obtained plane waves, we obtained Bessel beams, Gaussian beams, spherical harmonics, etc. So these are all the kinds of solutions that satisfy the homogeneous wave equation in the absence of any scatterer. Okay? So now our objective for today's lecture and for the entire spring term is actually to find the scattered fields, the additional fields produced by this object. When the incident fields hit that object, it induces certain currents, charges, polarization in that object, and these currents, they start radiating. And we're going to learn different tools that allow us to find this bad boy, the scattered field that arises due to the interaction of the object with the incident field. So the total field, which consists of the two, it is incident plus scattered, satisfy the same wave equation, but with a different permittivity. Now it is the full permittivity epsilon, which is the sum of, well, it's not the sum, it's just the full permittivity, which accounts for both the environment and the presence of the object. Okay, so now let us do a trick that will lead us to some kind of formal solution that will shed light on the properties of the scattered field. Let's split the permittivity into two contributions. Let's define delta epsilon, which is the difference, the perturbation of the host permittivity by the scatterer. So this is epsilon scatterer. Let's say if we have glass, then epsilon scatterer is 1.5 squared. And if it is surrounded by air, this is just 1. So we subtract from the full permittivity of the object the permittivity of the environment. And this is our delta epsilon. And let's plug this delta epsilon here. So we will, instead of epsilon, we will write epsilon host plus delta epsilon. And we still have the full electric field here. And now we do the trick. Now, besides this substitution, we do another substitution. We expand the electric field here as the sum of two components. Total fields equals scattered plus incident. And then, when we do this trick, we recall that the incident field satisfies the homogeneous wave equation with this guy, with epsilon host, right? So when we substitute epsilon for this, and when we substitute electric fields with this, some terms in this equation will cancel, and that will lead us to that. This is the result of this manipulation. So here we have what looks like wave equation for free space. Notice we have only epsilon host here. We do not have epsilon of the object. This is permittivity of the host medium, of the environment. And this acts on the scattered fields. And then we have something on the right-hand side. And this has been a very important manipulation in these equations. This is one of the crucial steps in formally solving the scattering problem. So let us look at that equation one more time. Let us try to understand what we have done to this equation, the meaning of this manipulation. So what we have done is that we manipulated a homogeneous equation with 0 on the right-hand side with some incidence fields to another equation with a source term. So this, what we have on the right-hand side of the wave equation, is just source. This is current density. Remember, the wave equation is written like curl, double curl, minus epsilon a squared E equals, I don't remember the signs and the factors, but this is something like minus I omega mu naught J, where J describes the electric current density. So with this manipulation, we managed to reduce this equation to something that has what looks like some effective current density on the right-hand side. And this current density itself depends on the scattered field. So we arrived at a formal equation that couples the scattered fields by this trick on the left and on the right hand side. So, and this is essentially the equivalence principle that we discussed with you on one of our first lectures. What we have done is that we replaced the presence of the object that was described by a certain permittivity, permeability, refractive indices, to a set of charges, currents, elementary electric currents that are distributed in the volume of our object with certain density, with certain weight function. There is no object any longer. We don't have the object. What we have in this equation is simply certain current density. Because here, in the entire space, we have only Hopf permittivity. There is no epsilon s in the equation, right? We don't have it. What we have the homogeneous environments. We have simple homogeneous medium. And we have certain source, J. We can just replace this by J and agree that J implies this monstrosity. And of course, we have to remember the fact that this J itself depends on the scattered field. So all in all, we arrive at the form of equation that couples the scattered fields through its right and left-hand sides. And in principle, now we can formally try to solve this equation, because this essentially, it's not a scattering problem any longer. This is a radiation problem. And we know already how to solve the radiation problem. We learned that just a few lectures ago, right? All we need to know is the Green's tensor of our system. And in this case, the system is just homogeneous environment with a constant real-valued permittivity. This is like Green's tensor, Green's tensor of free space, but with a different permittivity. We know the tensor, and we know the current. Well, we don't know the scattered fields yet, but we know the expression. So formally, we can plug this guy, into the Green's tensor formalism and obtain expression for the scattered fields. And if we do this, if we apply the Green's tensor of the medium, we end up with this. Something that looks like an integral equation, because the scattered field depends on the integral of entire space, integral with certain kernel function. In mathematics and in theory of integral equations, this is called kernel of the integral equation. And it depends on the scattered field itself. So this is a Fredholm integral equation, if I recall correctly, of the second kind. So what we have done so far is that we reduced our scattering problem to the radiation problem, which mathematically we managed to express as an integral equation. And now we need to try to solve that integral equation. And this equation is called the Lippmann-Schwinger equation. This is the central equation of the scattering theory for waves of any nature. This is completely universal, and it applies to electromagnetic waves, acoustic waves, water waves, quantum waves, elastic waves, pretty much anything. Okay, let us look at that equation one more time. So this is a linear equation, because the operator that relates scattered fields from on the right-hand side to the left-hand side, scattered fields to itself, is linear, luckily. So we can formally, this is by the way a graphical, just to recap, just to summarize, this is a graphical illustration of what we have done, how we transformed the scattering problem with some incident fields and with permittivity with the objects, with the scatterer, to a radiation problem that is characterized by a homogeneous space and a certain current density, which in turn, of course, depends on the scattered fields, and that establishes the coupled nature of this equation, and this has become possible thanks to the equivalence principle of electromagnetics. So let us rewrite the Lippmann-Schwinger equation in a slightly different form. Let's try to save space, and instead of that monstrosity with the Green's tensor and with volume integral, let us hide all that monstrosity into this fancy linear operator L. Because this is a linear operator, like I said, and we can denote it with some operator, right? And then the integral equation takes the following simple form. So formally, what we can now do is we can try to resolve this equation, just formally. Let's suppose we know this operator, what it does, how it acts on different vectors. And by the way, we haven't talked about the linear space on which this operator acts, but we'll talk about that later. And what we can do is that we can try to resolve this operator L, whose action is given by this expression. And if we do that, we can resolve this equation with respect to the scattered field and in principle obtain the answer. So if we do this, we manage to express the scattered fields through the incident fields, which is exactly what we wanted to begin with. And this answer is expressed by another linear operator S, which takes the following form. And this S is called the scattering operator. And this is formally the answer to the scattering problem. But the life is not so simple. If we look at the form of this scattering operator, it is absolutely unclear how we should approach finding this operator. I mean, what it is, we approximately more or less understand what L is, although we don't know yet on which vector space it acts. We have no idea how to inverse this operator. This is absolutely undoable. This is practically undoable. And then we need to multiply it by L one more time and understand how to represent this resulting monstrosity in... Okay, this is weird. Okay, then we're gonna... Now let me try another pen. Yeah. And then we need to understand, even if we manage to inverse these operators and to calculate their products, we need to understand in what vector space we can represent these operators. But despite all that, this is a formal solution, and formally it relates incident fields to the scatter field. Okay. But like I said, there are difficulties, and in practice, this problem of computing this operator is undoable for any realistic structure. And then there is another difficulty. Like I also said, any linear operator, it acts on certain vector space. It acts on a vector from a linear space. And we need to understand what that linear space is. In quantum mechanics, it's called Hilbert space. So I'm going to be using that terminology here as well. We need to understand in what Hilbert space we are working. These vectors, E incident and E scattered. Incident, scattered. What Hilbert space are they from, these vectors? Is it vector of just columns of numbers with 5, 10, 100 numbers, or is it vector space of functions? What is it? So in order to do that, to understand the nature of this linear space, we're gonna now introduce the concept of scattering channels, and this concept will allow us to introduce the highly useful concept of the scattering matrix. So let us expand incident fields and scattering fields over so-called scattering channels. So we're going to introduce these waves, E incident, E outgoing, called scattering channels or ports, as solutions of the wave equation in free space in the absence of scatterer with different boundary conditions. So basically, we're going to be looking for orthogonal set of waves that carry energy towards the structure from infinity and away from the structure towards infinity in the absence of any scatter. So these are the modes, these are the waves, solutions of wave equation that exist in free space, in homogeneous space, in the absence of our object. This is what carries energy from infinity. These are the basic solutions that constitute our incident fields. And they form a complete set, and therefore by using this set of solutions that only differ by the boundary conditions. Incident channels, they carry energy towards the object. Outgoing channels carry energy towards the infinity. And this complete set of solutions will serve us as a basis to expand the incident and the scattered field. And then when we expand, we will obtain a set of amplitude, scalar amplitudes. So these are the usual, these are the complex amplitude that characterize how a given incident and scattered fields is expanded into this set of channels that we have introduced. And if we do so, we can represent the relationship between the scattered and incident fields in the matrix form. Now, if we do this, we can write that E scattered, no, sorry, not E scattered, the S minus S outgoing, which is the set of all these complex amplitude, simply equals S matrix times S plus, where S plus is the vector of all incoming amplitudes. And this is the matrix formulation of the sketching problem. So what we have done by using these channels, this E incident and the outgoing, is that we projected, we fixed a certain linear space, a Hilbert space, in which we can consider the sketching problem. And then we projected the sketching matrix onto this set of channels, and that gave us the following relationship between the scattered and incident fields. And this is the graphical visualization of the sketching matrix. So we have a set of M channels that carry energy towards the system, and also the energy leaves the system via this channel in the opposite directions. And the object is some black box. Something happens inside this black box with incident radiation. We don't know what exactly yet, but something happens. Energy gets redistributed between different channels. So energy goes from here to here, maybe some will get absorbed, and so on and so forth. And these elements of the S matrix, they describe exactly the way in what electromagnetic energy between different channels gets redistributed from channel N to channel M, and so on and so forth. So this is the definition of the scattering channels, and typically what scattering channels are is this depends on the geometry of the problem, on the symmetry of the problem, and typically it is a set of plane waves, cylindrical harmonics, or spherical harmonics. For a planar system, the set of channels is usually plane waves incident on the system at different angles. For system with only one translational invariant direction, like a cylinder, it is a set of cylindrical harmonics. And for a system lacking any translationally invariant dimensions, for compact object like a nanoparticle, a sphere, a cube, it is convenient to work with a set of spherical harmonics. So these channels, for every channel, we have actually two waves. We have the incoming wave and the outgoing wave. And the fields of the incoming and outgoing channel are related by the time reversal operation, of course, because the outgoing version of a channel should simply be obtained as a time reversal of the incoming one. And if we know the complex fields of a certain channel, then the fields of the corresponding outgoing one, as we know, can be obtained by complex conjugating electric fields, and similarly for the magnetic fields. So one more thing to keep in mind about these channels is that we need to normalize these fields somehow. So these fields, E out, E in, they are solutions of the homogeneous wave equation, and the wave equation does not dictate any kind of normalization for them, but it is important because we need to have a unique procedure, unique rule that tells us how these fields are normalized so that the matrix elements of this matrix are given by the same rule, that they are in agreement with this rule. And one normalization that is particularly often is the set of flux normalized channels, which is expressed by the following identity. And what it tells us essentially is that the square magnitudes of these complex amplitudes of channels, they express the total energy flux carried away by the incoming or outgoing wave in a particular channel. So if you normalize your fields, where, by the way, H is the corresponding magnetic fields in a particular channel. So if you normalize your channels in this way, then the square of the absolute value will simply give you the energy flux carried towards the structure or away from the structure in a particular channel. And then this sort of, in a way, this fixes the gauge in which you express all these Ketchum matrix elements, and that provides a convenient way to calculate the S matrix coefficients. So this I think I should have placed it a couple slides ago. Sorry for the confusion, but now my presentation talks about actually expanding the fields into scattering channels. So we have expanded the fields already, the incident and outgoing fields. We do not expand the fields inside the structure. We basically don't know what happens inside the structure. This is a black box for us. What we do know is what happens outside the structure. And outside the structure, the field is carried toward the system by incoming channels and away from the system by outgoing channels. And we expand only the field outside the structure. And these two vectors, S plus and A minus, they describe the complex coefficients of the complex amplitude of incidence and outgoing wave in a particular channel. And then by projecting the relationship between the scattered and incidence fields onto these channels, we obtain the matrix formulation of the scattering problem, that S plus equals S matrix times S plus. And again, this is the graphical visualization of the problem, which I think is quite self-explanatory. Again, just to recap, we have some black box connected to a set of channels. Each channel carries one wave in, one wave out. The waves reach the system, something happens inside the black box, they mix with each other, and then they go out. And the S matrix, this linear operator, it completely captures this mixing of fields from different channels at every particular frequency, at every particular wavelength. Okay? And it completely describes what happens to the system when we look outside. It does not quite describe what happens to the fields inside. If we have the entire scattering matrix of an object written this way, for example, 2 by 2, 10 by 10 matrix, 100 by 100, we don't really know what happens to the system because S matrix relates only incoming fields to the outgoing ones. It reduces all the information about the system to this linear operator, and it does not tell us what happens to the fields inside the system. What form do they take inside the system? Are they getting focused to some place? Are they getting absorbed somewhere, etc., etc.? This only captures the relationship between incidence and scattered field. So this is S matrix one more time, basically the same expression written explicitly in the matrix notation, where we can explicitly see all the matrix elements. And this might remind you something. This looks a lot like something we have done already a few lectures back, the transfer matrix. The transfer matrix indeed looks, the transfer matrix formalism looks very similar. What we have in the transfer matrix is certain matrix T, which acts on a set of waves on one side of the system, usually it's on the left-hand side of the system, and returns another set of complex amplitudes, typically on the right-hand side of the system. And if you don't look carefully, you can think that they are similar, but the difference between these two approaches is fundamental. What S-matrix does is that it takes the complex amplitudes of incoming fields. S1 plus, S2 plus, etc., Sm plus, they are all incident onto the system. They carry energy towards the system. An action of the S-matrix tells you what is going outside, what is radiating away from the system towards the infinity. And all this information is encoded in the matrix element, so sketching matrix. Transfer matrix now is different. It takes what you have on the one side of the system, on the geometrical side. Typically, transfer matrices, they are applied to planar systems. So it takes what you have on the left-hand side and it gives you what you have on the right-hand side, irrespective of the direction. In this particular realization, which is one of the most common, you have one incident and one outgoing wave on the left-hand side, and correspondingly one outgoing and one incident wave on the other side, okay? And in principle, we can see from this how transfer matrix should be transformed in order to give the sketching matrix of the same elements of the structure. So what we need to do is that we need to modify these vectors and correspondingly t in such a way that on this side we have only incident, and the incident is A and D. So we need to move B to this side, and we need to move D to this side. So we need to flip these two vector elements, B and D. And this can be done by a unitary transformation of the transfer matrix, if I'm not mistaken. And then when we apply such transformation to this matrix, this will be a sketching matrix, because then what we have on this side of the identity of this expression will correspond to incoming radiation, and here we'll have the scattered radiation or outgoing waves. So there is a relationship between the S matrix and the transfer matrix, but you should not confuse them. They are fundamentally different objects. So in many situations, but not always, we can diagonalize the sketching matrix. And we can reduce it to diagonal form, which will have m elements on the diagonals, because we have m ports. Therefore, we're going to have generally m diagonal elements. And in the basis of the corresponding channels, so we can make a basis transformation to the new base of eigenvectors of S, and in that new base, the relationship between so S minus M will equal S acting on Sm plus, and that will simply be some scalar multiplied by the initial vector. So the vector of all incoming amplitudes, S plus, is simply modified by a scalar by the diagonal matrix element, and this gives you the vector of all outgoing waves. So the waves, of course, change from incoming to the outgoing, but the vector of complex coefficients, complex amplitudes, is simply modified by this scalar d. And every element can be written in the exponential form, where we have, which basically represents every diagonal element as the absolute value multiplied by some exponent, where this expresses the absolute value of this expression, describes the amplitude with which the scattering happens, and this delta describes the phase of the scattering, which you might be familiar from quantum mechanics. If you had scattering theory in quantum mechanics, then I suppose you had a very similar form of the scattering matrix coefficients in quantum mechanics course. Yeah, this is just explanation of this exponential form for the diagonal matrix elements. Like I said, the absolute value describes the magnitude transformation. It can be multiplied, can be enhanced or diminished by a certain factor. And delta in the exponent describes the additional phase that the scattered field acquires with respect to the incident field. So symmetries of the object, they are important. They determine the corresponding symmetries of the S matrix itself. For example, one of the most common symmetries is the passivity of the object, if the object does not have any loss or gain. And as we know, this is expressed by the following identities that impose constraints on the permittivity and permeability tensors. And by the way, I think I made have I done a mistake? I think that I have, because the criterion of absence of gain and loss is that tensors are Hermitian. Yeah, so these tensors must be Hermitian. And that means that the object preserves electromagnetic energy. No matter how much energy you send onto the object with your incident fields, the same amount should be scattered or reflected back in those channels. And that means that if our channels are flux normalized, if we are working in the flux normalized base, then the sum of electromagnetic fluxes overall incoming channels must equal the sum of the corresponding fluxes in the outgoing channels. And if we do a little bit of math, we'll arrive at the conclusion that this is equivalent to the S matrix being unitary. So S times S Hermitian conjugate equals unitary matrix. In other words, in terms of the eigenvalues of S, it means that every eigenvalue of S, if it can be diagonalized, every eigenvalue of S equals 1. Right. Another important constraint on the S matrix elements, which will play a significant role later, is the one that is imposed by reciprocity. So many systems that will be dealing with, in fact, almost all the structures that we'll be dealing with in the spring term are going to be reciprocal. And you remember that reciprocity means absence of static magnetization, absence of time modulation, and absence of any nonlinearity. And the scattering matrix is this property corresponds to a certain symmetry of the corresponding S matrix of the object. And to derive this property, to figure out how this symmetry is expressed mathematically, we need to do a little bit of math. We need to do some tricks. So it's a bit complicated, but bear with me. I'll try to explain how we derive this property. So let's consider an arbitrary scatter connected again to a number of scattering ports. 1, 2, 3, m doesn't matter. And let's consider arbitrary incident fields, two different states of incident fields, E incident prime and E incident double prime. These two fields are completely arbitrary and completely independent. This is one thought experiment and this is completely another thought experiment. So we simply illuminate this system with some combination of incident fields whose amplitudes S plus 1, etc., S plus m, we choose absolutely arbitrary, okay? We have no restriction on that. And then these electric fields are, of course, related to corresponding magnetic fields. And these two states of incident fields, E prime, E double prime, they produce corresponding scattered fields in the same channels, in the same channels. So radiation goes back. And of course, let's say we know what the sketching matrix is. If the sketching matrix is S, then it establishes the connection S minus equals S times S plus. So once we know the incident fields, we also know the scattered fields. And I already assumed that I can expand all my fields, electric and magnetic, over this set of channels. So because E prime consists of two components, it has incident and scattered, the expansion of E prime is going to look like this. It has the incident components described by this set of amplitudes, and has the outgoing or scattered component described by this set of amplitudes, analogously for the magnetic fields, and analogously for E double prime, H double prime. I didn't write down all the set of expressions because it is completely unnecessary. So now we're going to apply the reciprocity theorem. So reciprocity, if the system is reciprocal, requires that the following combination must be 0. And the integral of this combination over the volume of the system must be 0. This is a trivial property. This is trivial consequence of reciprocity, or the fact that permittivity and permeability tensors are symmetric. So I remind you that reciprocity implies that epsilon equals epsilon t and mu equals mu t, where t stands for transpose operator. And what we do then is that we take this identity and we integrate it over this volume that contains entirely, that encloses our structure. The volume, I will denote it as omega, and the boundary of this volume is d omega. And then I'm going to integrate this, and in order to integrate this, I apply Gauss's theorem, which allows me to reduce the integral over volume to the integral over the surface. And then I'm also going to apply the orthogonality condition for the channels, which looks like d omega. So it's 1/2 real part electric fields P times HP conjugated equals Q equals delta PQ. This is the normalization condition for the fields that describe our sketching channels. This is very tedious, meticulous, I know, but you have to get through this. I'll get you through this. So we perform integration, and when we integrate over d omega, we get rid of all the electric fields. We only have the amplitudes. So we have this. So these are the complex coefficients that describe incoming and outgoing fields in all the channels that we have in our system. And then we recall that outgoing channels, outgoing amplitudes can be obtained simply with the action of the sketching matrix for prime and for double prime. S acting on S plus double prime, this step. And then we do just one more manipulation, and we obtain this. This is the consequence of reciprocity theorem. We just assumed that reciprocity theorem holds, and then we did some mathematical manipulations with channels, with Gauss's theorem, and with this sum, all right? But because these input fields for prime and for double prime are chosen absolutely arbitrary. Remember, like I said, in these thought experiments, E prime and D double prime is absolutely arbitrary. And therefore, these vectors, these sets of complex amplitudes, also can be absolutely arbitrary. That necessarily means that S must equal S transpose. And this is the main consequence of reciprocity. In other words, the sketching matrix of any reciprocal system is symmetric. This is one of the most fundamental symmetry that S matrix of any object can have, well, along with unitarity. So just to recap the last two statements. If the system is a remission, if it doesn't lose or gain energy, the S matrix is unitary. And if the system is a reciprocal, which happens perhaps I would say more often than unitarity, then the scattering matrix is symmetric. Right, so that's the basics of the scattering matrix. And now let us talk just a little bit about what can happen in non-reciprocal systems. What can happen to the S matrix in non-reciprocal systems, and then we're going to forget about non-reciprocal systems for a good while. So one example of a non-reciprocal system that is often occurs quite often in practice is the so-called optical isolator. So an optical isolator is a system that is capable of transmitting energy, electromagnetic energy, from port P into port Q, but is not capable of transmitting energy in the opposite direction, from port Q to port P. So another way, it has S from P to Q. The second index is where from, and the first index is where to, right? So SQP does not equal 0, SPQ at the same time equals 0, and obviously this violates the symmetry property that we just established a minute ago. It means that SPQ does not equal SQP, so S does not equal ST. So the system must be non-reciprocal in order to enable optical isolation, right? As simple as that. And in practice, optical isolation is usually achieved by, well, there are two mechanisms basically that are popular. It's either magneto-optical effects, Faraday optical isolators, where non-reciprocity is achieved by statically magnetizing the system with biasing the system with a static magnetic fields, or by temporarily modulating the system at very high rates, which also breaks reciprocity and allows optical isolation. Some kind of extension of the optical isolator is the thing called optical circulator. So as the title suggests, what optical circulator does is that it circulates energy between ports in one direction. So this figure shows the example of N-port circulator, a very general concept. And so what it does is when the energy is supplied to the system through port 1, the system sends it to port 2. When the energy is incident through port 2, it goes to port 3, etc., etc. In the simplest case, it can be a 3-port circulator when there are only 3 ports, 1 to 3, and the energy cycles like this. 1 to 2, 2 to 1, 3 sent to 1, and then the cycle repeats. And if we consider the simple example of 3-port circulator, the S matrix takes the following form. So this is transmission from this is from 2 to 1, this is from 3 to 2, and that is from 1 to 3. Yeah, this is the S matrix that describes kind of the opposite circulation, but doesn't matter, you get the idea. This S matrix is of course not symmetric. If you transpose it, you're not going to obtain the same. It violates reciprocity, and therefore, in order to obtain an optical circulator, we're gonna need a non-reciprocal system. And again, the popular choices for obtaining optical circulation are biasing with static fields or time modulation. Let's see what happens if we now take a bunch of optical isolators, identical optical isolators, and arrange them in a lattice, in any kind of lattice. Square, triangular, hexagonal, doesn't matter. It just has to be identical isolators, and they're going to have an edge somewhere in space. Okay, we have only so many circulators. And then this happens. So because in every circulator the energy circulates in one direction, this is what's going to happen to electromagnetic energy in the entire system. So this illustrates schematically energy flow in any given circulator. The energy circulates in one direction along the circulator, in this case clockwise. And so it cannot penetrate inside. If we excite the system here at this point, if we inject energy at this point, it's going to circulate along the edge, and it simply cannot go inside the system because every circulator forbids, it does not allow the energy go inside the system. And let's also say somehow we prevent the radiation from leakage to the environment, to the outside, for example, by closing it with some metallic walls or something. Does it remind you anything? This is a quantum Hall effect in solid state that can be realized for electrons. And what I just described to you is a photonic analog of the quantum Hall effect, which is called a topological insulator. So what we have is a photonic system represented by a lattice of non-reciprocal elements, optical circulators, that enable one-directional topologically protected transport of electromagnetic energy along an edge. So that creates a one-way propagating edge state immune against scattering by disorder imperfections. And such a system is called a photonic topological insulator. And again, there are at least two ways to achieve photonic topological insulation in photonics. Just like there are two ways to achieve optical isolation and circulation, you can realize this with static magnetic field, in which case this is called quantum Hall effect topological insulator, or by modulating the system in time, in which case it will be called a Flaquet topological insulator. There is a third way which bases on properties on spin properties of bioisotropic system. This is called spin Hall topological insulator, and as the title suggests, it is closely related to the spin Hall effect in solid state. And so there is another concept, quite similar concept, yet a concept that should not be confused with optical isolators. And that is the concept of optical diets. So what an optical diet is, what it does is that it takes energy as an input and it transmits it to the other side. And on the other side, it can transmit into a lot of channels, into a number of channels, not necessarily one. It can diffract, scatter, can form an outgoing spherical wave, anything. So what we do is that we record the intensity transmission coefficient, power transmission coefficient. We set energy, we send some energy in, and we monitor how much power is transmitted totally, irrespective of the scattering channels. And then what we do, we inject light on the other side of the system, for example, by a plane wave propagating on the other side. Let's say this is one plane wave, and this is another plane wave propagating in the opposite direction. And then we measure the same. We measure how much intensity is transmitted to the other side of the system. And it may happen that on the other side, there will be almost no intensity upon illumination from this side. And at first, it might look like optical isolation, but it is not. Because what we look here for is a symmetric power flow. It's only power, it's the intensity that we care about in the case of optical diets. We do not care about the individual elements of the scattering matrix. So we don't need to verify that we have different SPQ and different SQP. We don't need that. What we care about is only the power flow, and furthermore, it's not power flow in a single channel, that can be power flow across many channels. Let's say this is a diffraction grating. Radiation incidents on this side of the system can diffract into this set of channels, and what we need in this case is to suppress the total intensity that we can record on this side of the system. And a structure that realizes this functionality, that produces asymmetric power flow, is called an optical diet. And because we don't care about violating the S-matrix symmetry, it does not require reciprocity. So optical diodes are possible in completely reciprocal systems. So this is basically an explanation of what I just presented to you. It says that, just once again, that we monitor the intensity propagating from one side to another, from side A to side B, and from side B to side A. And unequal transmitted powers, unequal power transmission amplitudes will say that we have an optical diet. And to give you an example of an optical diet of a completely reciprocal system that features the optical diet functionality, consider this. So this is a lens with an array of slits. And no, this is not an array of slits. This is an array of sources. Sorry, these are sources. These are elementary sources. And on this side too. So what we do, and we place a slit in the focal spots of that lens on one side. And then we illuminate the system from this side. The lens focuses radiation to the spot. Radiation, almost entire radiation passes through the slit, of course, through the aperture. And then we have almost near complete transmission of this radiation to this side. So we can say that T 1 to 2, this is nearly 1. And then what we do, we illuminate the same system from the other side. And this aperture, because it is placed before the lens, it blocks almost all of the radiation, and only a tiny fraction of the radiation passes through the aperture and passes through the lens. And therefore T to 1 will be nearly 0. This is an example of an optical diet. Completely reciprocal system. There is no magnetic field, no nonlinearity, and no time modulation. Yet it achieves a functionality of an optical diet. And with this, I would like to conclude today's lecture. So what we learned today is that we can solve an arbitrary scattering problem formally by considering the Lippmann-Schwinger equation and by formally inversing the operators, linear operators that enter that equation. And by doing so, we obtain the scattering operator. And then we can describe a complete set of scattering channels. And by projecting the scattering matrix on this set of channels, by representing this scattering operator in the set, we obtain the scattering matrix, which explicitly relates complex amplitudes of incoming and outgoing waves. So now the question, of course, is how do we calculate this actually? What we're going to do to calculate this, to calculate its matrix elements. And this is going to be the subject of the entire spring term when we're going to talk about developing different models for solving the scattering problems analytically, semi-analytically, phenomenologically, and we're going to explore different effects, different resonant scattering effects that can be encountered in different Hermitian and non-Hermitian systems. So that is all for today. Thank you for your attention.